welcome to the demo session on FPGA-based signal processing system. I am Saurabh Kumar, working under the guidance of Professor P. Sumati and TA for this course. Today's demo, we will be implementing some combinational circuit that was covered in the lecture on ZedBoard. We will be using sliding switch for giving the input, and to check the output, we will be using the LEDs from this board. Also, we will be demonstrating how to write the constraint file for a circuit. Search for the Vivado icon in your desktop, double click on it, automatically it will open. So it is AMD Vivado ML edition 2025.1. Now you just click on the create project. So this new project window will pop up, in which click on next. So here you just define your project name. Now I am writing it test gate, and it will be saved in the project location C user admin desktop and nptel demo. Just click on create project directory. It will be creating your subdirectory like source file and constraint file in the same project directory, which is at the location user admin desktop nptel demo. Click on next. We will be creating the RTL project. Please uncheck this two things, that we are not specifying any source this time, and the project is not extensible BTS platform. You click on next. Here we can create a source file. Just I am creating, like the language should be Verilog, and I am just writing test gate. So the file name will be test gate, and we'll click on OK button. It will automatically save to the in the project directory itself. Now click on next. Here you can add the constraint file, it's optional, but we are going to implement it on ZedBoard, but we have to write the constraint file also. For this time, I am skipping it now. Click next. This is the very crucial step. In that, you have to select the board. Just select ZedBoard. So this will come. Just on the preview section, double click on it. Board will automatically appear over here. You can match this board image with your current board. Suppose in that section, if your board is not there, just click on refresh button. Automatically, it will download the latest catalog from the AMD site. Click on finish. Here you can check the summary of your project, what you have created, in which you have created the RTL project. Name is testgate. We have added a source file over there. No constraint file added at this time. And this is the board default board name. And since ZedBoard is from Zinc 7000 family, it will come like Zinc 7000. Package will be CGL484, and it has a speed grade of -1. We click on finish. So it will initialize the project. There will be a pop-up showing that define module. You can define the module name here itself. So the module name, by default, it will take as testgate what we have created in the directory. We'll click on OK. So the module definition has not been changed. Okay, I'll skipping it for now. I'm not defining the input output here. So it is updating. Now, in the flow navigator, you can check that we have setting, we have IP catalog, you can create the block diagram, we have simulation over there where you can run the simulation, behavioral simulation, we have RTL section, we have synthesis, implementation, and a program and debug section. In the source, you can check that, okay, you have your design file here, you can add your constraint, you can add your simulation file here. So if you double click on the testgate.b, automatically it will appear in the editor window, where you can check that module testgate is already created because we have given the name testgate, and here module and end module will come. So for this, you need 2 input and 1 output, because I'm testing 2 input AND gate input, and I am taking input A and B, and the output will be by. Now since I am using the primitive gate, just write AND, and you can give the gate name also here, and it will be output followed by the inputs A, comma B. Just take care of that. It is a case sensitive language, so if you are using capital A, it should be a capital A everywhere. It should not be the small, or it should not be mixed. So it will be closed by the semicolon. See, now I have created a AND gate by using primitive AND gate. The name is G1, output is Y, and input is A and B, which is already defined inside the module, that I am taking input as A and B, and output will be by. Just save it. So it is updating over here. So if it's not popping any error, so our code is correct. You can check your code by clicking on RTL analysis section. Just click on run linter. It will give, if your code having any violation in your writing style, or you have missed anything, So here in the pop-up, you can say that no violation found. This code is met all the design rules and it has no violation of this one. Now, after that, just open the open elaborated design section, click OK. So it will take some time depending upon your processor, and it will initialize reading low. It will load the device. Now, if you expand this section, it will come report methodology, report DRC, report noise schematic. Methodology will give any violation in your code. DRC design rule check at initial level. Click on the schematic. It will be shown over here in the schematic section, where you can see that we have AND gate, we have two input A and B, and output is connected to by. And just click on the input output planning over here. If it is in default, just click on the input output planning, and this input output planning will be open like this. So in this section, you can say that we have three ports, three scalar port A, B, and by. A, B is input and by is output. Now we have to connect this A and B to our FPGA board so that it can take the input from a sliding switch in the FPGA board, and output can be seen from the LEDs in that board. Now for that, you need to define the package pin. Just have a look on this board. This board having 8 sliding switch, and we have LEDs to check the output. We have some push button also, it can be used for giving the input. So for A, I am giving the input from this switch, first switch, and you can check that number, it is F22. So I am defining here A is input and it will be from F22. Just click on F, it will come F22, and it should run on LB CMOS 18, means it is low voltage CMOS at 1.8 volt of logic. Again, for similarly for B, just check that second port, it is G22 for this sliding switch. We'll select G22 over here, okay, G22. And again, this will run on LBCMOS 18. We'll check that LBCMOS 18 over there as a IO standard. And by is the output. It can be seen from the LEDs. And we'll check that these are the LEDs having package pin as T22. So we'll define T22 over here. And it will also run on low voltage CMOS at 1.8 volt of logic. Okay, this all for input output planning for this circuit. We'll save it, Control S. So this save constraint will pop up, in which file type will be XDC file, and you can give the file name as like test gate constraint. We'll save it, click OK, it will automatically save. Now just click on the sources, click on the constraint, and if you open that test gate constraint, it will be written like this: set property package pin F22 gate port A, means our signal A is fed from F22, that is a sliding switch in our FPGA board. Get port A, it will be running on LB CMOS 18, means it will run on low voltage CMOS 1.8 volt of logic as IO standard. Again, B will be fed by G22 package pin, that is sliding switch in our FPGA, and it will also run on LB CMOS 18 as 1.8 volt of logic, and output can be seen from T22, that is from that is LED on the FPGA board, and it will also run on LB CMOS 1.8 volt of logic as IO standard. So it will automatically return like this. Okay, we'll save it. We'll click on the run synthesis. So this launch run will pop up. Here you can select the launch the directory. It will automatically save in the same directory where project is created. Will launch on the local host. We'll click and OK. So it start running. It starts synthesizing your code. You can check the status over here, running synthesis design. So it will do the methodology check. It will check for any violation. It will, in the synthesis level, it will convert your RTL into FPGA netlist. So that netlist will be used for implementation in the next stage. It will take some time depending upon, again, your processor of your system. So you can always check the status over here, running synthesis design. Okay, so once synthesis will complete, one pop-up will appear again, synthesis completed. We have successfully completed our synthesis. So we'll go ahead with the implementation one. Just click OK. Again, this pop-up will launch, pop-up will come, we'll click on OK, it start the implementation part. Now, meanwhile, if you click on open synthesize design, we click OK. So it will open your design in here itself. This is the synthesized design for your code. Now, if you expand, you can check the data flow model design of your code, like the logic end its interconnection by clicking Open Data Flow Design. You can check the timing summary, you can check the report clock network. If suppose we have multiple clock, since it is a combination circuit, we don't have any clock. So if we have multiple clock, it can be seen from report clock network. If how our clock is interacting with each other, it will be on report clock interaction. Again, methodology, it will check for any violation in the synthesis level. The design rule check will give the violation. Noise utilization, you can check how many LUTs, how many block RAM, how many DSP your code is using. In the report utilization section, you can check the early power, like report power. It will give the static and dynamic power your code will be taking. On the FPGA board, you can check the symmetric overhead by clicking the symmetric button. So we have successfully implemented our design. We can go ahead with the bitstream generation. We'll click on the generate bitstream and OK. Again, if you expand the implementation part, so this all will thing again appear as constraint wizard, in timing. It will be on the implementation level. So you can check that. Okay, again, constraint wizard, you can check for any violation, data flow model. You can have a like view of your logic level and interaction in the implementation. After synthesis, you can edit the constraint also. You can check the timing summary. You can check the number of clocks and how it is interacting with report clock interaction. You can check the methodology, and the design rule check will be happen at implementation level also. You can check the final utilization, how many LUTs, block RAM or DSP your code is using. You can check the final power, how much power it will take on FPGA board from report power. And you can check the technology schematic by clicking on schematic in this section after implementation. Now, we have successfully generated the bitstream, means it's a configuration file for your FPGA. Directly will feed this configuration file to the board for further implementation. This will be successfully only after you don't have any critical warning or any error. So if bitstream is generated successfully, means your code is working fine, it don't have any critical warning or the error. They'll click on the hardware manager. Before that, just connect your board with a 12-volt 3-amp power supply from in this socket, and this board will be communicating through your PC by JTAG, and it will be type B to type A connection. Type B will go to the JTAG of this board, and type A will be connected to the PC. Now just turn it on. This LEDs will glow, means your board is turned on. This is the power LEDs. We'll click on Open Hardware Manager. So it will open the Hardware Manager. Now just check there is no hardware target is open. We'll click Open Target and auto connected. So if it is connected through JTAG, automatically it will get connected to the localhost server. Now you can see that our board it is connected to the PC and it is not programmed over here. You can see that it is showing that Axis 7Z02_1, it is not programmed. So we'll click on program device. So this bit file automatically will appear. It will be saved in during the bit file generation in the project directory. So just check that test_get.bit. We'll click on this file, it will be programmed. Now once the board is programmed, this blue LEDs will glow. Now we'll check that, okay, I am implementing the AND gate. We have given the input from this to sliding switch and output can be seen from this LED. Now just check that it is 0, 0, output will be 0 as AND gate. 0, 1, 0, it is still 0, 0, 1, it is still 0. And if we give 1, 1, this will glow, means for 1, 1, output will be 1 in the AND gate. So moving to the next program, we'll open the next program as new, we'll open it. All gate. So in this program, I have implemented all the gate like AND, NAND, OR, NOR, XOR, XNOR in one file. We'll dump that code in our board and check its functionality. Now it will open, it is updating in the source, in the design source, all gate. Just double click on that. You will check that, okay, this is a module named all gate. We have to input A and B followed by the outputs AND, OR, NOR, NAND, NOR, XNOR and XOR. Now, since in this code we will using primitive gate, that AND gate we are using output will be AND and A and B. Similarly, OR, NOT, NAND and XOR. Now to save the time, I had already generated a bitstream. Before that, we'll have a look of the constraint file. We'll open this constraint file. Now here we have two input, A and B. It is connected with the package pin F22, G22. That is the sliding switch on our FPGA board, and it will be running on IO standard LV CMOS 18, like low voltage CMOS 1.8 volt of logic. Similarly, to check the output, it is connected with the LEDs in our board with the package pin T22, and it will be for AND, and it will be running on LV CMOS 1.8 again. Similarly, for T21 is the second LEDs, U21, U22, U21, B22, W22, and U19. It will be the LEDs on the FPGA board. Now, since I have already generated the bit stream, bit directly head on the Open Hardware Manager, click on that. Since no hardware is detected here, we'll click on Open Target and Auto Connect. So it will be connecting to server again. This board is connected. Okay, you can check that. Now the status is programmed. Since this board is programmed with the previous one, we can override this by clicking on Program Devices. Again, this bit file will come. We'll click on the program. Now our board is programmed with this all gate logic we have implemented in this. So see, we are going to take the input from A and B. So if we give A and B at 0, 0, AND gate will be 0, and NAND gate will be 1, and XOR will be 0. So if we give 1, 0, see, again the AND gate will be 0, since AND gate will be active only when all the inputs are 1. So it will be 0, NAND will be 1, and XOR will blink, means it will be 1. Now again for the 1, 0, same, you can check that OR gate, AND gate, NOR gate, everything. For 1, 1, you can check that AND gate will blink. It will be on, but XOR will be off, since 2 input is 1, 1, XOR output will be 0. This all the gate verification, you can verify by switching the sliding switch and giving the A and B as input from the sliding switch, and the output it can be seen from this LEDs. Like this is for AND gate, this is for NAND gate, this is for XOR gate. Now moving to the next program. So let's open the half adder. I'll opening the half adder, click on OK. We'll close the previous demo. Okay, it is updating over here. Now double click on half adder. I am using a half adder having input A and B, and the output as sum and Cout. Now the sum will be XOR of A and B, and the carry out will be the AND of A and B. Now click on the constraint file. If you open the constraint file, here we have 2 input as A and B, and it is mapped with the package pin F22 and G22 on this FPGA, and this will be running on again IO standard as LV CMOS 18, means 1.8 volt of logic. Similarly, Cout can be T22, means the first LED is on this board, and the sum will be seen on T21, means the second LED is on this board, and all this will be running on LV CMOS 18, means 1.8 volt of logic. Since I have already generated the bit stream to save some time, so we'll click on Open Hardware Manager, Open Target, Auto Connect. It will again connect it to the this board will connect it to the PC. It will show like this board is programmed, since we have programmed with the previous one. We'll overwrite by clicking on Program Devices. Half adder.bit will come. You will click on the program. Again, this board will be programmed. Now you can check that if it's 0, 0, sum and carry will be 0. It will give 1, 0. This sum XOR will be glowing, means sum will be 1 and carry will be 0. And again, if we give a 0, 1, again the sum will be 1 and carry will be 0. For 1, 1, you can check that sum will be 0 and the carry will be 1. Now, moving to the next one. Now, I am using that half adder to design a full adder. We'll click on the full adder by half adder. Okay, we'll close the previous one. So now it is updating. So once it updated, you can check that. You can click on the full adder using half adder in the module full adder using half adder. That the module name. I'm taking 3 input here, A, B, and carry in, and the output is sum and Cout. Intermediate wire I have taken at W1, W2, and W3, since we are using 2 half adder 1, half adder 2. That the name will be G0 and G1. Now since we are using half adder here, we have to define its path over there with /include. This is the path for our half adder. Now if we click on Open Elaborated Design, click on OK. So the schematic will open, the gate level and logic level connection will open. You can verify here also. We'll click on the schematic. You can check that this 2 half adder. If you expand this, it will be AND gate and the XOR gate. This half adder is connected with another, and this Cout will be the OR gate of this one. This is already covered in the lecture slide. We'll directly go ahead with the implementation one. Since I have already generated the bitstream, let's have a look on the constraint file of this one. So if I double click on constraint file, it will open like this. So we have 3 input here. So the 3 input will be F22, G22 and S22. These are the package pin on FPGA board for the sliding switch, and all 3 will be running on LBCMOS 18, means 1.8 volt of logic. Similarly, the output can be seen on T22 and T21 LEDs on the FPGA board. T22, the first will be for C out and second will be for sum. And since I had already generated the bit string, open hardware manager, automatically it will appear no hardware target detected. We'll click on open target, auto connect. Now the board is connected, it will show the okay, this board is programmed with the previous one. We can overwrite it by clicking program devices, .bit file, just click on the program. It will be, this program will dump in the FPGA board. Now you can check that. Now the input is 0, 0, 0. There will be no sum and no carry. If I give the carry as 1, see the sum will be 1 and the C out will be 0. Again, if I give B as 1 and carry in as 0, then sum again it will be 1 and the C out will be 0. Similarly, you can check for other option also, like 1, 0, 0. You can check for 1, 1, 0. For 1, 1, 0, you can check that the sum will be 1 and the, the carry will be 1 and the sum will be 0. Since it's a XOR and you have 2, 1, so XOR will be 0. Now for 1, 1, 1, you can check that the output will be, the C out is also 1 and the sum is also 1. Now moving to the next program, we'll open. So now we'll check the mux multiplexer. Open it, we'll open the XPR file, we'll give OK, we'll close the previous one. Now it is updating. Now you double click on this. We are taking a module named multiplexer. I am taking 2 input as X1 and X2 and 1 select line as S. Output will be F. This intermediate wire, this is already covered in your lecture slide. And if I click on the constraint file, we'll check that, okay, we have one output F. It can be seen from T22 port, that's the first LED on the FPGA board, and it will be running on LBCMOS 13 again. This input will be fed S, X1 and X2 by F22, G22 and H22. The see, this one is F22, the first will be F22, means S should be this line. The first sliding switch will act as the select line. This is the second one. G22 will be the X1. This is the G22. This is for X1. This is for X2. Now we'll program this. I had already created. You can check the open elaborated design over here. The RTL of this code, like the logic and its interconnection. You can just click on symmetric. It will be look like this. So we have 2 AND gate and then 1 OR gate for this multiplexer. This X1 and X2, this is the select line. Now if I click on the open hardware manager, we'll click on the program device, auto connect. So the board will get connected with the PC. It is programmed over here. We can overwrite it. Click on the program devices, program. So it is programming the devices. Now it gets programmed. Again, this LED will confirm that your board is reprogrammed again. So this is the select line. This is X1 and X2. If the select line is 0, this will be 0. We don't have any input. So if I give the X1 as 1 and select it 0, then this LEDs will glow again. It will not affect in this one since selected 0. Again, if I give the select as 1, this output will glow. If we give the X2 as 1, this will be glowing. So you can check that if pitch select is 1, this output will give by sliding the switch 0 to 1, and it will not affect from this one. Okay, this is for 2:1 multiplexer. Now moving to the 4:1 multiplexer. This is the 4:1 multiplexer. We'll open the XPR file. We'll close the previous one. Now just expand the mux 4:1. Here you can see that we are using now 4 input. Since it's a 4:1 multiplexer. For 4 input, we should have a 2 select line, that is 1:0. It means we have 2 bit and output is output. Again, we have some intermediate wire. And if you click on the constraint file over there, it will be like this. So again, A0, A1, A2 and A3, these are the input. and it can be fed from F22, F21, H22, G22 and F22 on FPGA board from the sliding switch, and all will be running on 1.8 volt of logic. Again, the output can be seen on T22, the first LED on this FPGA board. Now we'll click on the generate bits, or since I had already generated the bit stream, we'll click on open hardware manager, we'll click on open target, auto connect. So it will get connected. Now these are the select line. So it is programmed. Since this will be confirmed, this board is programmed now. 1, 2, 3, 4, these are the input. You can verify it by the code, and it will be like if par select is 0, 0, this will be 1, and this will be by changing the sliding switch, you can check that this is the first input, second, third and fourth. This is the select line. Now moving to the next program. Next program is the prime number detector. Now with just double click on prime number detector, just head to XPR file, click on OK. You'll close the previous one. Now double click on the prime number detector. This is already in the lecture slide. Ma'am has already covered this. We'll click on the constraint file, double click on that. You can check that we have 4 input here. A0, A1, A2 and A3. These are the input. This can be fed from this package pin F21, H22, G22 and F22 from our board. And the output can be seen on the T22, the first port. If the prime is get detected, the LED will glow. Otherwise, it will be turned off. Okay. Since I have already generated, you can check the design also from elaborate design section. We'll click on that. Click on the symmetric. You can check that RTL symmetric over there. It's interconnection. Now, since I had already generated the bit stream, it can be seen on this section. We'll click on open hardware manager. Click on OK. Click program device, auto connect. Okay, now it is saying that the board is already programmed with the previous one. We can rewrite it by program devices. We click on program. It will program the device that can be seen from this LEDs. The blue LEDs will glow. Now, if I give the input like 1, 1, 1, see, it will glow like this 13, 1, 1, 0, 1. It will be 13. It will glow. Like same way, you can check the output by changing the input from this sliding switch, and you can check the output. If its prime number get detected, this LEDs will glow, otherwise it will be turned off. Thank you. This is all for the first demo. We have implemented some combinational circuit that is already covered in the lecture slide on ZedBoard, and we have verified its functionality by giving the input from sliding switch, and output we are checking on the LEDs.